Thank you, William. Very good introduction. Thank you. Thank you everybody coming over to spend your afternoon of Saturday, listen to some technical talks. Hopefully it's not too boring. Let me share my slides. Hopefully you can see. So I will give you some introduction on the NAND flash and some new applications. I'm not gonna bore you with many old applications. So this is a regular, some safe harbor forward-looking statement. I will skip this. So I will give you some introduction, what's going on in this storage and memory domain. And then I will give you some introduction on the 3D NAND flash scaling. And then I will talk about some of the new flash applications. So first of all, introduction. Many of our speakers already said that, our previous two speakers all talk about big data. So here we have big data in the zettabyte creation. We create the data every day, take a picture, video. So actually lots of data is not able to save because we do have a limited storage. The first speaker talked about edge, and we also have some endpoint, and then edge and cloud is major categories. So normally the edge and endpoint cost money. So lots of people, when you buy iPhone, you don't want to pay a lot of money for 256 gigabyte or 1 terabyte type of storage, because iPhone, how much you pay is absolutely depends on the flash memory inside, how big of capacity. So everybody tried to save their stuff on the cloud now, but still we have so much stuff is not really data created versus data stored. It's actually we have a very little amount of data get stored in reality. It's because the storage has been very expensive. I will talk about that. Actually, Western Digital is in the business generating storage. And in terms of storage, I want to give you a little bit the computing hierarchy. Normally, our previous speaker, Bill, talked about CPU. And then at the bottom, further bottom we go is usually getting cheaper, but usually we need more of them. So so after the CPU cache is very close to CPU and is very expensive, but we cannot make lots of them. And then DRAM is a second, and storage class memory like Intel's Optane. So we are in the business of NAND and HDD, Western Digital. I'm particularly today gonna just talk about NAND because I'm working in the flash side. So you can see this pyramid, regardless which area of this pyramid, we need more of them. But DRAM actually not scaling anymore. Our previous speaker also talked about Moore's law. It's very hard to scale DRAM. So I want to just show you NAND, we are continuous scaling and we don't see some limitations. We're still following the Moore's law. So this, I will give you some more detailed descriptions. So certainly Western Digital produce lots of product from all the way from card to like a computer you use in the computer to the data center. So I will go a little bit faster, focus on, let's talk about the NAND flash scaling. So as I discussed, previously mentioned is we are still continue scaling. DRAM already slowed down scaling, and then even the CMOS transistor on the CPU or GPU, scaling is very expensive. The previous speaker also talked about that. So for us, we actually not really just growing 2D dimension, we are growing in the 3D dimension. As you can see, a normal transistor is have a gate, have a drain and a source. This is a normal transistor. If you add a floating gate, that would be a flash. So the definition of a flash memory is you have a floating gate in the configuration of a transistor. So this floating gate will store the electron charge, and then after the power off, this electrons being trapped in the floating gate. They're not going anywhere. That's how we store the data in the flash memory. So as we scaling, we cannot continue with this 2D NAND scaling anymore because we don't want to using like EUV. Previous speaker also talked about EUV being very expensive. For us, we also facing not only the lithography problem, we also facing the geometry problem. The floating gate getting too small and cannot store enough charge. And so losing charge will be very bad. So where we go, we are going circular. And not only we go 3D, but we also do a cylindrical. The cylindrical cell is actually very nice because it's a circle. If you lose a charge in the X, Y dimension, you kind of lose to yourself. So it's not called the losing charge. And the only Z direction, maybe you're losing charge. That's being counted a loss. So this also, we can make the cylinder very big, much bigger than the 2D NAND size. So we can take advantage of this memory cell in a cylindrical form, and we can build a big tall building like high skyscraper. So make this NAND string very, very long. And also this also benefiting on the process side. We don't have to build each layer independently. We actually build this tall building in less steps than making every layer available. So this is how it, we find the 5th generation, 6th generation. So the engine of a 3D NAND revolution is, as I said, is a cylindrical cell. But another thing is that we are changing to charge trap cell. Charge trapping is much easier to make a 3D. So we have as many cells as this sand. Is just an unbelievable amount of cells we are making at this moment. So you can see each program performance. We try to increase the performance each generation by 20%. So the write performance is most important. Certainly, read performance is also important, but write performance is related how fast you can write a big file into the storage. So we usually talk about the program performance. We are increasing at the speed of 20% per generation. On the other hand, we also have a logical scaling, like we have a 2D NAND. TLC is 3 bits per cell, and QLC is 4 bits per cell. So 3D NAND definitely had an advantage. 4 bits per cell usually have a lower reliability than the 3 bits per cell because we stuck too many bits in one physical cell. But you can see the 3D NAND, the reliability, performance, okay, this is talk about program performance. But if program performance and reliability, the 3D NAND's QLC, 4 bits per cell, is equal to the 2D NAND, 3 bits per cell. That's quite a bit significant change. In some sense, is kind of a 3D NAND give us another big expansion in terms of performance and quality, in terms of flash reliability and performance. So let's talk about the scaling. CMOS scaling is always shrink, shrink, shrink. And you look at the linear dimension, is it like a 10 nanometer, 5 nanometer, or 3 nanometer? So the NAND dimension became a different level of scaling. We talk about layers. We're growing the skyscraper ever higher, 48 layer, 64 layer, 96 layer. You can see this, the tall building is continuous growing. Not only that, we also scaling, this is the one dimension scaling, is called vertical scaling. And then we also have a lateral scaling. So we kind of squeeze the memory hole to be tighter, closer together. and also get rid of the overhead. And architecture-wise, we also have a dramatic changes from the CMOS not overlapping with the memory array to the CMOS, which is our peripheral circuit. It will be overlapping with the array. So on the other hand, we also have a logical scaling down below here. So as I said, I already talked about 3 bits per cell and 4 bits per cell. We also have single bits per cell and double bits per cell. And we have all these, and maybe we will go to 5 bits per cell. We're stacking more bits per physical cell. So this is about the scaling. This is a 4 vectors of the 3D NAND scaling. It's not a very just a one-dimensional scaling. We talk about all kinds of different scaling with the different generations. So the previous speaker also talked about the expensive. I mean, semiconductor, it is getting more expensive. It is also true for 3D NAND. 3D NAND is building this tall skyscraper. It is very expensive. So you can see that the capital expense just means equipment. We buy the equipment to etching the memory hole and to building all the memory layers. It's getting more and more expensive. So you can see that just for 1% bit growth, and the money-wise is really growing dramatically over the years. And we forecast is going to continue to grow. But each manufacturer, we have 5 flash vendors in the world, but each flash vendors maybe have different strategies dealing with this expense. Some people are thinking much more cost effective production of NAND. So certainly, all these capex, we pay the money to Lam Research and Applied Materials. They really have the most gain out of this NAND flash growth and NAND manufacture. But in the future, we heavily rely on the vendor. That means equipment vendor actually supply the technology for us for growth. As I said, maybe we are continually grow, but in some ways we rely on the Lam Research and Applied Materials to supply the tools for us to grow. We are foreseeing you can grow down to 500, no problem. Actually, we already foresee the 500 layer is not that far away. So we grow, many architecture changes and on logical physical scaling. So there's many factors, but the good news is NAND is continuous scaling. Okay, let me talk about some of the NAND flash applications, what we see in the Flash Memory Summit this year. Some of them is from previous years, but I just give you some introduction, what's the new trend in general. So as you know, maybe know the SSD is built like this. You have a SSD controller and you have a bunch of memories, NAND flash memories. NAND flash memory is not easy to manage. It's not like a DRAM, it's not like SRAM, it's not a byte addressable memory. It's a kind of you have to erase by block. That's why you need a complicated SSD controller. And also NAND has lots of failures and you have lots of errors generated. You read one page, maybe you have lots of errors, you have to correct it. So you need some ECC engine to build into this controller. So usually controller have lots of processors, normally use ARM processor. And then we also can connecting with the DRAM for a buffer or internal SRAM buffer. But this block management actually is causing lots of trouble for the customer because the flash controller and not only when the host want to store something in the NAND memory, they have to go through the SSD controller. And some of the things that SSD controller has to do in the background, like we call it flash management, like shuffling some blocks and defragmentation and data buffering and wear leveling. You have to kind of wear the memory uniformly and also have to handle error handling. So some of the customers don't like that. So they say, I have a mission critical mission. I want to write the data or read data right away out of the NAND flash, but you are blocking me because you are doing all your housekeeping jobs of or doing this and that. So that slowed down my performance. So lots of people don't really like this traditional way of SSD. That's why we are migrating. Not everybody migrating. I'm just saying specific applications. And some people want to do the software manage the NAND, but that's come out to be very difficult because there's too many things to manage, and the software cannot handle all these, take over all these jobs. And then we have an intermediate solution, so-called the Zoom namespace. So instead of everybody have lots of application randomly writing everywhere, so you have to do defrag if you have a retired data, if you have application goes out. So what we are saying that you can be very disciplined, dividing the memory into different zones. And you can see that originally, the conventional SSD controller, you have application 1, 2, 3, and they are all mixed matched. So when you retire one memory and then you have to have lots of blocks, is very fragmented. So if you do this zone namespace, and you are more disciplined to write the same application in the same block, so you can erase them or retire them altogether. So you don't have to be fragmenting the storage all over the place. So this is the so-called zone namespace. This has been going on for a few years, and I think are gaining much more momentum right now. This also can give us another edge of using QLC, 4 bits per cell instead of 3 bits per cell for many more applications. So another application we use, this is new. Actually, we win the Flash Memory Summit 2022 product award. And in the HDD, we actually put in the some of Flash to help manage. This actually is called the OptiNAND, has broken through the conventional boundary of storage, adding to Western Digital's legacy of industry first technology. So it's actually bring up lots of new features for the HDD. So lots of people talk about the data center, and data center certainly have lots of CPU, GPU, but there's tons of SSD and HDD and connectors. So these are basic components of a data center. You can see there's lots of architecture migration recent years. In the old days, you pack is like a unit. The unit, you will have a CPU, you have a GPU, you have a SSD, HDD, and then connect all together as a unit. And then everybody independent unit, you just increasing unit in the data center. And then we found out this is not very flexible because some company like a Facebook, they have a very dynamic applications, and sometimes this application is very busy, and sometimes the other application is very busy. Each application actually have a different requirement for CPU, GPU, and even SSD requirement. So what they end up with is we are migrating to called the disaggregated infrastructure. That means I'm going to separate things. I'm going to separate the CPU and lump the CPU, GPU together, and then lump the Flash and HDD together. This is a more dynamically configurable infrastructure for the data center, especially you have lots of dynamic load in a different time. I have a different application running at different like a workload and different intensity. So you can configure really very easily in this one. So I think there's a newer one, like some other people produce some specific chips, not a CPU or GPU. They are doing like a more data DPU, they call it. So this is a new configuration, but I think most people are still doing the conventional or disaggregated. Disaggregated infrastructure is gaining much more momentum. So that's actually needed to increase the I/O speed for Flash or for SSD. So you can see the PCIe, the spec is growing dramatically over the years. That's also forced our NAND interface growing over the years dramatically. Over 30% node over node transition on the interface speed. So this is a very dramatic increase over the past 10 years. So another new interface coming to our way, so proposed by Intel is the CXL interface. So in this Flash Memory Summit, Samsung presented this new architecture to supporting AI machine learning applications. As our previous speaker also mentioned, AI machine learning also adding more and more parameters. The parameter increase over the complicated AI machine learning applications growing dramatically. That's need a lot more memory. But the DRAM, as I said, is no longer able to scale that well. They're not going to increase the capacity that dramatically that fast. But NAND could. NAND still scaling very fast. So we have to leverage the NAND flash and using the new CXL interface to supply the big data into the AI machine learning application. So this is part of the architecture. We can using DRAM to be the buffer, but we can using NAND to supply most of the data in a very configurable way. So on the other side, the big data has created lots of big data is also very difficult problem to handle. It's very big, it's growing, it's valuable. But moving data is very expensive and power hungry, and it's good to minimize it. So moving data means, when we do the conventional architecture, all the data have to move to CPU or GPU get processed. So that's why the power is a big problem. And we're moving all the data in and out, and all the data has to transfer. So the conventional architecture, computer architecture, always doing this way still. So right now we are thinking, this is a new trend, definitely. We want to move compute to storage. So reduce all these big data movement. But certainly this computational storage has been also talked about it for many years. And I think it gradually gain more momentum. We have more standardized protocols to handle this. And it will be beneficial. It's only things much more complicated for software to handle. Software people is sometimes very hard to change their software. And actually hardware change is much easier than software change. So that's why this trend is still not coming, even though lots of people already work on it. So some of the specific computation we can download, like a compression, deduplication, encryption, erasure code to protect your data, and some of deep learning. And many people already work on it. And we are seeing the trend is gradually more and more people moving in this direction. But this big data definitely need this trend to keep going this way, because we cannot afford to move every data in and out of CPU and GPU. And we have to locally process the data and make sure the movement is less, because all the data movement is very power hungry. All right. I want to summarize my talk, and as I said, NAND continue to scale to meet big data demands, and the technology is viable and need a lot of investment to continue the scaling. This is a challenge for the industry overall. And big data era and need a lot of new architecture to solve the big data problem. And so it's data-centric architecture is evolving rapidly. Computation will move closer to the data for energy saving, and lots of new protocols and new architectures are emerging. I would say this is a very, still very exciting field to be in. So we welcome more people who join us in this exciting industry. Thank you.
Oh, thank you, Yan. That's extremely educational and very helpful. I used to support many different SSD controller customers, but I guess today is the first time I appreciate the challenges. And you mentioned HDD, NAND, That's, for those of us who used to work on a hard disk drive, 20 years ago, that was kind of like a back to future. So, but I want to congratulate you on being the winner of the 4th annual Super Women in Flash Leadership Award. For those of us who couldn't attend the award ceremony, that's back in July, can you share with us the highlights of your accomplishment that caught the attention of many?
Yeah. So thank you for raise this question. It's a good question, and I think it's really is a privilege to be the winner of the we call the Super Woman of Flash in the Flash Memory Summit. It's really a honor to get this award. So I think first of all, I work in this industry for the past 25 years. And definitely there's a lots of exciting technology has been developed in this 25 years, which I'm a part of it. So I can say 2 significant contributions. One thing is, we worked on the so-called orbit line architecture, which is double the write performance. So that's also enables all these logical scaling, like from like a MLC is a 2 bits per cell to 3 bits per cell, and then eventually to 4 bits per cell. So this contribution is mainly, Flash Memory Summit is very product driven. So this is just contributing to for apply more of the logical scaling to the NAND flash applications. The second contribution is more on the sort of a reliability side, and we have a lots of coding and what kind of coding is have enhanced the reliability. So it's I would feel my career is very blessed because I'm working in the golden years of NAND flash, and it's have a lots of patents, which these patents actually impacted the products. I'm very, very lucky to be in the right time, actually, at the right place. Thank you.